Good afternoon. I am Danilo Renzo from Sapienza University of Rome, and the title of this presentation is Application of Game Theory-Based Interpretability Method to Machine Learning Algorithm used to predict the fatigue life of the additive manufacturing alloys. The aims of research is develop a methodology for the data preparation of heterogeneous multimaterial dataset. At second, apply machine learning techniques to multimaterial dataset for predicting the stress ambito that is linked to fatigue life in additive manufacturing components, and develop a framework that ensures the high interpretability and reveals the predictive interdependence between features. I will start with an introduction about the multimaterial used in this study, and after I will explain the methodology for data preparation. This step is very important not only for the machine learning training, but also for the model interpretability analysis that is based on Shapley value theory, and we developed also a code for the analyze the cooperation synergy between pairs of features. At the end, I will show the result and conclusion. The database used in this study was provided by Zhang et al. And this database contained data about different data area, about material type, additive manufacturing process parameters, heat treatment surface finish, fatigue test parameters, and static mechanical properties. We have considered only the features that influence the fatigue line inside this database. In the table are in red color. And in addition, the features processing sequence and parameters was divided in three more detailed features. In particular, orthostatic press treatment and heat treatment and surface finish. This database was at first loaded in a PyCharm environment, and after we applied the methodology, we start with the data cleaning step to delete MB row and duplicated data. In the next step, we apply data encoding and standardization. Data encoding was carried out using one-hot encoding function that converts each unique categorical value in a binary new column. No difference was observed for the best performing algorithm if you change functions such as label encoding. And the standardization was carried out using the standard scale function that transfer the data in the normal distribution with mean equal to 0 and the standard deviation equal to 1. In the last step, we analyzed the variance, and in the final database was built using the sub-dataset of various alloys with highest variance. In particular, with data about titanium 6 aluminum for vanadium, Inconel 718, and 316 steel alloy, and aluminum silicium 10 manganese alloy. In this table, we have the input features that remain after the last step, and the total number is 14. And in the figure, we have the different datasets for the 4 different materials that are contained in this database. The choice of machine learning algorithm adopted in this study was made considering the published research study that indicated the best performing model in the predicted the fatigue behavior for several additive manufacturing alloy. In particular, are all supervised machine learning algorithms, such as linear regression, rigid regression, kernel rigid regression. Also tree-based models such as decision tree, random forest, extreme gradient boosting, and other models such as KNN, Gaussian process regression, and also assemble algorithms such as voting regression algorithm that combine multiple regression model to improve the predicted performance of individual model by combining their prediction. The hyperparameter optimization was carried out using the bias-aversive method that helped to explore the hyperparameters for each algorithm. And in the figure, we have the partial dependence plot for extreme gradient boosting and KRR. And in particular, the out diagonal subplot display the partial dependent plot for that influences the performance of the model of various hyperparameters, and in a non-diagonal subplot we have the interaction between pairs of hyperparameters. The training and the validation was carried out using the kappa-fold cross method. This consists to divide the data set in k groups, namely folds. And during each iteration, a distinct fold is used as a training set, and the remaining folds are used as a training. At the end of all iteration, each fold was used one time as a test set, and in the other times as a training set. To evaluate the performance of each algorithm was considering the span of value to predict. We decided to use several standard metrics like coefficient of determination, mean absolute error, and root mean square error. Considering the background knowledge, it is evident there exists a nonlinear relationship between the selected features and the stress amplitude our target. In addition, it is known that nonlinear relation between the stress amplitude and the number of cycles to failure is defined by Basquiat law. This is a power law that can be rewritten in logarithm form as a linear function. This expedient was also used in other study. And therefore, we asked two different type of algorithm to predict the logarithm value of stress amplitude. And the best performing algorithm was Kellner-Ritchie regression, with I give the highest R squared score equal to 0.956 and lowest mean absolute error and root mean square error. Together this, we also other algorithms give similar performance, such as extreme gradient boosting, deep neural network, and voting regression. In this case, Kellner-Ritchie regression and extreme gradient boosting approach the deep neural network performance because they effectively capture moderately nonlinear patterns. In contrast, deep neural network typically require larger and more diverse dataset to fully exploit the expressive capacity and surpass the simpler models. Considering the goal to have a consistent interpretability approach across different algorithms, the sharply additive explanation method is a was-used method, and the sharp framework is a model agnostic and provides both global and local interpretability, allowing for an in-depth analysis of the impact of individual features on specific prediction. This is based on cooperative game theory. And in this slide, we have the result, the sharp value result for extreme gradient boost. In the figure, each dot corresponds to an individual data sample. The color of each dot reflects the magnitude of the feature value. A broader spread along the horizontal axis indicates a strong influence of the model output for a given features. And in the figure on the right, we have the bar plot, and we can observe the rank of this analysis, the importance rank of this analysis. This rank was used in the features interdependence analysis. The figures show the outcome of the sequential feature selection process based on the result of SHAP applied to predict the logarithm value of stress amplitude using the extreme gradient boosting. And we can observe that the model give the best performers, not using all input features, but only 12. A deep level of interpretability was carried out using developed code to analyze the cooperation synergy between pairs of features. This code produced a map. This map illustrates the interdependence between pairs of features, and we can observe the number of synergistic pairs of features is 20. Whereas the number of conflicting pairs of the features is 71, with cooperation referred to the positive prediction synergy between features pairs. In addition, we can observe the scan speed is the feature with the highest synergic capacity with the other type of features, based also on physical reason. And in this slide, we have the result for energy regression. The map showed that the number of synergic pairs of features is 11, and also in this case, scan speed is the feature with the strongest synergic capacity. And the figure about the sequential feature selection show that the model achieve the best performance using, in this case, all input features, 14. In this slide, we have the binarized matrix, and the cell in red color indicate the rebel pairs or features, and in green, the cell in green color indicate the features that find the cooperation and are able to achieve good performance, both for extreme gradient boost and energy regression. Why we have cooperate or rebel? Because in absence of sufficient predict signal from feature space, regularization learning in energy regression on not split and split learning in extreme gradient boost tend to suboptimal result rather than a synergic effect to achieve good performance. In this slide, we have the result for the deep neural network, and you can observe that the figures about sequential feature selection show the model achieve the best performance using, in this case, 13 input features. And in this slide, we have the map about the analysis of cooperation synergy between pairs of features. And we can observe that in this case, deep neural network provide the highest number of positive synergic values with respect to energy regression and extreme gradient boosting. In this case, the number of synergic pairs of features is 31. And it is because deep neural network is able to extract useful information and achieve relative high performance, thanks to the adaptability of this model that's able to find correlation that remain hidden to more rigid approach. And in this case, we have the features with the strongest synergic capacity are scan speed and the name of a material. In conclusion, the study introduces a methodology advanced in heterogeneous multi-material data preparation, model interpretability, and machine learning prediction of stress amplitude that linked with the fatigue life of the human factory components. Sharp values framework and the synergic analysis provide particular effect in identifying key features and their interaction, offering insight of features cooperation impact prediction quality. In particular, the developed code for the synergic analysis enables the exploration of two features coalization and the assessment of their cooperative strength in predicting the target. Future developments consist in modifying this code to allow us to study the stability of cooperation synergy over the time. In particular, during the training, each cross-validation fold can be seen as a repeated independent game. And in this case, the algorithm identifies the features that cooperate well across the multiple rounds and will reward, while those that rebel are penalized, updating the file interaction matrix accordingly. Initial results are reported in this slide for extreme gradient boosting, and this is the study of temporal stability of cooperation synergies. And in the box, we have the map of features that find the cooperation in all fonts, in all rounds. The advantage of this analysis that can make strategy to improve the performance of each model, considering the couple of figures that are stable during all folds of the training. Thanks for attention.